Okay, still lecture 2 is cylindrical coordinates. You see, today is March, okay, I'm sorry. Today is March 3, 2025. Okay, this remarks, I put like that. You see, here, cylindrical coordinates, that's orange. This is my point Q. This is my point P. This is R. This is the polar angle theta. Okay, this is rho, OQ, okay, and this is Z. The Cartesian coordinates, let's put x1, x2, and x3. You see, Z belongs to Cartesian coordinates or rectangular coordinates and cylindrical coordinates. Okay? Now we see that R is equal x1 E1 plus x2 E2 plus x3 E3. Since R is invariant, then I can write here. Okay, before doing that, let's express x1, x2, x3 in terms of cylindrical coordinates. If you remember, I have rho cosine theta E1 plus rho sine theta E2 plus, let's put Z E3, you see? Now, do you remember the basis, for instance, okay, let's call A rho. You see, I will use that important property that I emphasized when I derived the Cartesian coordinates, rectangular coordinates. You see, A rho is partial R with respect to rho. That's a very, very, very important property, okay, that will be using in this case on the curvilinear coordinates, okay. So now the partial derivative, you see, rho, I emphasize that theta and Z, they remain fixed, okay? So I just look at here, when I derive that, I have cosine E1 plus sine E2. This is 0, okay? This is a rho, okay? Now, A theta. Theta is partial of R with respect to theta. This R and Z remains constant. You just look at here and derive with respect to theta. So this will be minus rho sine theta E1. You see, the derivative of cosine is minus sine. You see, rho is constant. Plus rho, derivative of sine is cosine, E2. And derivative of z, E3, is 0. So this is my A theta. Now do you remember? Then I define, I'll write down AZ here, okay, just to complete this row over here. So AZ, which is E3, you see, that's a derivative of this with respect to z. Look at that. Partial of rho cosine theta is 0 with respect to z. Let's write it here. Partial r with respect to z, which remains constant, rho and theta. You see? Just is consistent whether I emphasize when I showed, okay, rectangular coordinates, okay, the derivative of vector position, okay, leads to the base vectors, okay, on the correspondent coordinate system. So I just derive here with respect to z. Okay, this will be 0, okay, because rho theta, they are considered constant. This will be 0, so this over here is partial of z with respect to z, okay, E3. So this is E3, okay. Now, you remember, if I want an orthonormal basis using cylindrical coordinates, I just divide this by rho, you see? Then, do you remember? Then I have a rho, I'll call a rho here, a rho, I call E sub rho. A theta is equal rho, you see, I would, as I said, I will derive a theta. So E theta is equal A theta divided by rho. You see, I come here and divide by rho. So this will be minus sine theta E1 plus cosine theta E2. This will be cosine theta E1 plus sine theta E2. Then I have this two vector. So these lead to the orthonormal base vector in cylindrical coordinate. So what is the orthonormal basis? It will be rho, A theta, and EZ. Okay? These are orthonormal. I can see here, there's a point here, that's orange, okay? This I have my cylindrical coordinates. This is a rho. This theta. This is z. You see, they are orthonormal, okay, basis. There's a O, there's a point P over here. See, don't forget that there is a position vector, okay, at this point P. Okay. So this is enough for a while. Okay.